In this video, we're going to start talking about symmetry groups. So what we're doing is we're going to apply geometric transformations to geometric figures that have some symmetry to them. Now, some of this is review, but a geometric figure is symmetric with respect to a particular transformation if and only if the figure is mapped back to the same figure collectively by the transformation. Some individual points may or may not be fixed. They have the same preimage as image if they're fixed, but collectively the set of points comprising the geometric figures remains the same set of points in its image, even though some or maybe even all the points of the figure have been moved around by the transformation, moved individually, but collectively they stay the same. Such a transformation is called a symmetry of the figure. A symmetry is a particular transformation that leaves a set of points collectively the same. We say that a geometric figure is symmetric with respect to that transformation. Notice that the identity transformation is always a trivial symmetry of any geometric figure. If that's the only symmetry of the figure, then we do not consider the figure to be a symmetric figure. Since a symmetry of a figure collectively maps the set of points comprising the figure back onto the same set of points, the composition of two symmetries of a particular geometric figure is another symmetry of that same figure, making composition of symmetries of a particular geometric figure a closed binary operation on the symmetries. Every isometry has an inverse isometry. The inverse of a symmetry is another symmetry. We already know that composition of functions, including isometries and symmetries, is associative, and this is enough to show that the set of symmetries of any particular geometric figure with composition forms a group. So these are known as symmetry groups. So let's start with maybe one of the most obvious examples, the symmetry group of a circle. So a circle is a plane figure that has an extreme amount of symmetry. Circle is symmetric with respect to the identity transformation, of course, as any figure is, and also it's symmetric about any rotation centered at the center of the circle by any angle amount. So that's infinitely many rotational symmetries right there. But it also has reflective symmetry about any line, mirror line that goes in the plane that goes through the center of the circle. So there's also infinitely many reflection lines, reflective symmetries. So this set of symmetries forms a non-abelian infinite group. Notice that if we restrict this to the subgroup of rotations about the center point and the identity transformation, then we have a proper subgroup of the symmetries of the circle called the group of rotational symmetries of the circle. Let's investigate that a little bit with this activity here. Okay, so here we have, let's look at what happens with the image. So I've got a point, let's see. I've got R that controls the radius, X is the center. So we have our circle there. And I can move this line anywhere that I want it. And notice that here is A, and there's the image A prime, which is back on the circle. And this would be for any point that you pick, the image would be back on the circle, and eventually you're going to get every point on the circle. So no matter where I put that line, when we reflect the circle about that line, well, the 2 points that are on the line and the circle will be fixed. Other points will move, like A goes to A prime, but then A prime is going to go to A. They just swap places. And so that's going to be a symmetry of the circle because the circle stays the circle collectively when we reflect it about that line. And again, there are infinitely many of these lines, any of these lines that go through that point. Now, if we pick a different line, so here's a line here, and if I reflect the circle about that line, reflect that circle about that line. Notice now that image, let's give it a different color. That image is not the original circle, right? So, it can't be just any line, right? But if that line goes through the center of the circle, yep, it works. Okay. Similarly, we can take a rotation about the center of the circle. Here I can fix the angle and notice that the point B rotates to B prime. B prime will rotate over here somewhere, but the point is no matter what point you have on the circle, it rotates to something else on the circle. And so that collectively the circle is rotating around, but it still is the same set of points at the end. So that's a symmetry. And this can be any angle that we want um, with positive or negative rotations. Okay. All right. What about symmetries of regular polygons? So in general, symmetries, humans tend to respond to order and patterns of objects that have some form of symmetry. Many designs make use of symmetric elements within their design, and one basic class of figures that have a great deal of symmetry is a set of regular polygons. Recall that a regular polygon has all of its sides congruent to each other and all of its interior angles congruent to each other. Because of this, each regular polygon has several symmetries. They include reflective symmetries about lines through each vertex in the center of the polygon and about lines through the midpoints of sides in the center of the polygon. They also include rotations centered at the center of the regular polygon, which take a vertex to another vertex. One way you can define the center of a polygon is the intersection of all its diagonals. No, that's not right. Not diagonals. The intersection of these lines of symmetry. Okay. Since regular polygons are all cyclic polygons, the symmetric group of a regular polygon is a finite group of the symmetry group of its circumscribed circle. So notice that that center is going to be both the incenter and the circumcenter. It's the intersection of the angle bisectors, which makes it the center of an inscribed circle, the incenter. It's also the intersection of the perpendicular bisectors of the sides, which is a the center of a circumscribed circle. Those are the same center. That's the center of the regular polygon. Those would be, well, those things might not even exist for other polygons, and if they do exist, they may not be the same. Okay, but for regular polygons, they do work. So if we label each vertex with numbers 1, 2, up to n in a clockwise fashion, then we can label these line symmetries M1, M2, Mn, where n's the number of sides of the polygon. In the case of an odd number of sides, this results in n distinct reflections, with the line of symmetry going through a vertex, the center of the polygon, and the midpoint of the opposite side. If n is even, then this results in n divided by 2 distinct reflections, with the line of symmetry going through the opposite vertices in the center of the polygon. And then in the even number size case, there are also n divided by 2 additional lines of symmetries, where the line of symmetry goes through midpoints of opposite sides of the polygon at center. In either case, there are n reflections. We'll look at this in just a minute. In addition, there are n-1 rotational symmetries found by rotating the polygon through an angle about the center. The smallest positive angular rotational symmetry is 2 pi over n, or 360 degrees over n, and the other rotational symmetries can be found as rotations through integer multiples of that same amount. Of course, there's always the identity transformation as well, resulting in no points changing their positions. This brings the total number of isometries of a regular n-gon to 2n. The group of these symmetries of a regular n-gon is known as the dihedral group of order 2n. We will denote it as d sub 2n. However, note that some authors call this d sub n instead, so there's sort of two camps at which way that's notated. Notice that a dihedral group of order 2n has a subgroup formed by including the identity and all the rotations. This rotational subgroup is a cyclic group of order n. So let's look at this activity here, and we can see some of these things here. So I have some regular polygons. I can control the number of sides, and we should be able to look at the symmetries. So the least you can get is 3 sides. Notice if we reflect about a line containing the midpoint of one side and in the opposite vertex, then it's going to land back where it starts. So I can actually see that by actually doing the reflection here. So if I can reflect that about this one here, it came out to be the same thing. Other lines, may not reflect. You can reflect about them, but you may not get the same thing back. So here's a line here. If I take this figure here and reflect about this line, I get a figure here. Let's make it red. So this one, reflecting about this line, is not a symmetry because we didn't end up at the same place, right? So now if the line goes through this point and the vertex, yeah, that's going to work. If it goes through the opposite side and the vertex, if it goes through this side and this vertex, yeah, that's going to work, right? But just in general, they don't work, for all vertices, all lines. Okay. What about rotational symmetries? Well, the rotation that takes vertex 1 to 2, which is that angle turns out to be 120 degrees, that's the smallest amount of rotation. That same rotation will take 2 to 3. So let's actually see if we can rotate this. So I tell you what, let's do this. Let's add something to this. Let's add a slider. Let's make it an angle slider. Okay, it's beta. Let's do an input box to go with it. We can call that beta. And link that to angle beta. Okay, let me do a couple things here. I don't like the length of that box, so I'm going to make that 5. That's enough. And then we don't need to show the label on this one because I've got it below. Okay, so we got an input box slider combination. Let's take this and make a center point. Yeah, let's rename that Y. And let's take this figure and rotate it, this figure about that point, by angle beta. And make that red. Okay, well that's clearly not. Now if I do a 360-degree rotation about any point, it's going to be back to the same, but that's just everything ends up exactly where it comes, so that's the identity transformation, which is a symmetry, but it is the identity transformation. But even if I make Y and X the same, some people misunderstand how far this rotation goes. For example, they may say, well, it's not 120, but maybe 60 degrees. But see, that doesn't land on top of the original one. So that's not a symmetry. But if we rotate 120 degrees, it does. Multiples of 120 will also work. 240 degrees will also get us there, which is really essentially the same as negative 200, negative 120. Okay, so what if we go to 4 sides? Let's go to 5 sides. 5 sides is very similar. Okay, the lines of symmetry go through the midpoint of a side and an opposite vertex. So this is the odd case. And going from one vertex to the next, that angle there, which is 2 pi divided by 5, or 180 degrees divided by 5, that's 72 degrees, is the smallest rotational angle. So again, if I, try to rotate by something here, if it's not the right center, it doesn't really matter. I could go to 72 degrees here, but not with that center, and it's not, it still doesn't line up. But if I line it right up on there, yeah, that does line up. Any multiple of that is going to work as well. 144, that's the same. Negative 72, that will give us the same thing, and so forth. So there are lots of different possibilities there that will work out to be a symmetry. Any multiple of that particular smallest one. Okay. Now, when we go back to 4, it's a little bit different situation, but basically the same. We have 4 lines of symmetry. So remember, with 3, we had 3 lines of symmetry. With 5 sides, we had 5 lines of symmetry. With 4, we do have 4 lines of symmetry, but when we go through a point here, we don't go through, there's not an opposite side, there's an opposite vertex. So there are 2 lines of symmetry that go through vertices, in this case contain the 2 diagonals, but then midpoints of opposite sides here will end up going through there and be another place where we have rotational symmetry. So it's not 45 degrees here, but rather 90 degrees that will take you around. And if I rotate that, I'm going to get another square. But it's only going to line up if I match these the same, and I need to get the angle correct. See, if I go 45 degrees, nah, it doesn't match up, right? But what about 90 degrees? Yeah, that matches up the same. Or twice of that, 180 degrees. Or 3 times that, 270 degrees. And so forth. So we can see that. Okay? So let me just move that out of the way. And you can see there's 3 sides, which is the least number you can make for a polygon. That's going to give you a dihedral group of order 6, 3 reflections, 2 rotations, and the identity. 4 sides, that's going to give you a dihedral group of order 8. That gives you 4 sides, but also 4 reflective symmetries, 4 mirror lines, and 1, 2, 3 different rotations and the identity. 5, dihedral group of order 10, because there are 5 reflections, 4 rotations, and the identity. There's the ones for 6, 7, 8, and this just continues up. I've got all of them here, all the way up to 28, all the way to 30 actually. Hard to tell the 30 side one apart from a circle, but and of course since these are points on this, I've got it in kind of lightly here, the circumscribed circle. They are this is a subgroup of that group of symmetries of the circle, of that particular circle. Okay, now we can combine by composition these rotations and or reflections that are symmetries in a chain to obtain new symmetries of the polygon. And unlike earlier in the course, I'm going to switch to a right-handed notation. We will indicate the composition using right-handed multiplicative notation. So in this we have mirror 1, mirror 2 in that order. It says do mirror 1 first, then mirror 2. This is a change from what I did earlier. Okay. And then this particular product results in a rotation. Say if we do this one for through 2 times 360 degrees over n in the clockwise direction. Furthermore, notice that the angle between the two lines of symmetry, okay, is twice that, twice the angle of rotation. So it's a general result. Composing two reflections has the same effect as rotating the figure by an angle twice the size of the angle between the two lines of reflection, and with the center the same as the intersection of those two lines. We've seen this before. A composition of two rotations is also a rotation through the sum of the angles generating the original rotation. Two rotations about the same center, which is of course what we're dealing with here. Notice that other rotations and reflections, as well as all translations and glide reflections, will result in an image that is not the same set of points as the preimage. Therefore, these isometries do not appear in the group of symmetries of the regular polygons. You just have the 2n symmetries there. So if we label a rotation through an angle of pi over n, or 2 pi over n, 360 degrees over n, and the clockwise direction is r, or r1, then a rotation through k times 2 pi over n is just r composed with itself k times, which is what r to the k means. Now, it's useful to have another notation to consider here. So let's look at what happens here. If I rotate this by 360 degrees in the positive direction, vertex 1 goes to the location of vertex 2. Vertex 2 will end up where vertex 3 was. Vertex 3 will end up where 4 was. 4 will end up at 5, position 5. 5 will end up at 6, and 6 will end up at 1. So if we want to keep track of what's going on, since this is a linear transformation, we can really just keep track of what's happening to the vertices. So that particular one could be written this way: 1 going to 1, 2 going to 5, 3 going to 4, 4 going to 3, and 5 going to 6. That's a mapping, just telling us where the vertices go. This is called a permutation. So if we keep track of just what's happening to the vertices and seeing what mapping sends which vertex to which vertex, that is called a permutation of these vertices. So that's called a permutation. Now we have an even better way of notating permutations. So notice what happened here. 1 went to 1, 2 went to 5, 3 went to 4, 4 went to 3, 5 to 2. Okay, so what happens is that's a mirror image. So let's look at that one here. That's the mirror image about line 1. So that's the one that fixes 1. So notice this one's going to fix 1 and 4. Looks like we're on a hexagon here. So 1 and 4. Okay, but if we reflect about that line, 1 and 4 will be fixed. They're not moving. But 2 is going to go to 6, but 6 is going to go to 2. 3 is going to go to 5, 5 is going to 3. So 2, okay, so that's what we have here. 1 and 1 and let's see. Okay, this is a pentagon. Okay, so we're using this one here. This one here for a pentagon, if we reflect around this one, 1 is fixed, 2 goes to 5, 5 goes to 2, 3 goes to 4, and 4 goes to 3. That's what we have right here. 1 goes to 1, 2 goes to 5, 5 goes to 2, 3 goes to 4, 4 goes to 3. Okay, so one way to see this is to take a pentagon like this, cut it out, a copy of this, write 1, 2, 3, 4, 5 on the inside, and then actually pick it up and physically flip it over. then you'll see that the 5 is now here where the 2 was, the 2 is where the 5 was, and so forth. But a better notation for this is this. 2 goes to 5, which goes back to 2. That's written this way, 2 space 5, close the parentheses. So this says 2 goes to 5, 5 goes back to 2 in a cycle. 3 goes to 4, 4 goes back to 3 in that cycle. Notice we didn't mention 1 because it was fixed. So this is called cycle notation. Okay? We use the notation just a 1 to indicate the identity transformation where every point is left where it is. Every point's fixed. So a cycle 1, 2, 3, 4, 5 is a rotation, right? It's going to send 1 to 2, 2 to 3. So it goes 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 back to 1. That's the rotation, this 72-degree positive rotation about this center. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. It's a very compact, nice way of writing that, where we just keep track of the vertices. So that's a rotation of the pentagon through an angle of 2 pi over 5 or 72 degrees in the positive counterclockwise direction. Notice, however, that not just any listing of cycles will result in a actual symmetry. So 1, 2, 3, for example, that cycle doesn't work. 1 goes to 2, 2 goes to 3, and 3 goes back to 1. If you do that somehow and try to leave 4 and 5 alone, and you actually tried to do that, it just wouldn't work. It won't be a pentagon anymore, much less the same pentagon. Okay. So it's not physically possible to do that without completely distorting the polygon. So again, it turns out there are always two possible symmetries for any regular n-gon. Furthermore, the operations have some interesting basic properties. And let G be the set of symmetries of the regular polygon. Notice that the set of rotations from a dihedral group along with the identity forms a proper subgroup of the dihedral group. These groups of rotations are called cyclic groups. Cyclic groups have the least complex structure of any group. Cyclic groups can be thought of as powers of a single generating element. The set of natural numbers under addition is an infinite cyclic group. All finite cyclic groups can be thought of, or at least isomorphic to, the group of rotational symmetries of a regular polygon. This cyclic group is a subgroup of the group of symmetries of regular polygons, and in particular, a cyclic group of order n contains n elements that can all be thought of as powers of some particular generating one. In our case, R is that smallest amount of rotation from it sends 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 back to 1. That's 72-degree rotation. And all others are just powers of that. In other words, you do that, compose that with itself k times. And this is where R represents a rotation through 360 degrees over n, about the center of the regular n-gon. It turns out that dihedral groups can be generated from only two elements. If you start with the positive rotation, R or R1, that smallest positive rotation, and one of the mirrors, say the one that fixes the vertex 1, then all the elements of the group, in other words, all the symmetries, can be expressed in the form either R to the k or that m times R to the k for some whole number power of k less than n. And the key defining relationships that exist for this group are then R to the n is 1 is the identity. If you square m, that's 1. And R times m is m times R inverse. Notice in particular that the operation of the group is not commutative. Rm and Mr are not the same thing. So when you get, so these are typically not commutative groups. It's instructed to work out the details for the dihedral groups for orders for n equals 3, 4, and 5, orders 6, 8, and 10. And it's useful to have some physical things to do. So what I want you to do is try this out. So notice I have two triangles here. One has the numbers on the outside, one has the numbers on the inside. Cut out this one on the inside, print this out. Cut out this one on the inside with the numbers on the inside. Flip it over and write the numbers on the other side too. So the other side of this, on this vertex, write a 1, a 2, and a 3 on the other side here. Now put this in here with the 1 matching the 1, the 2, and the 2, and the 3, 3. And then do some transformation, like rotate it around, and you'll see that the inside 1 is here, the 2 is here, and the 3 is up here. Or you could do a flip where you leave the 1 fixed here, the 3 will be over here, and the 2 will be here. Okay, and similarly you can do that for the square here and for the pentagon here. That will help you with this assignment. So what I'd like you to do is I've drawn this here and I've written out what the symmetries are here and here, and what we want to do is do an operation table. And the way we're going to do this, we're going to apply this one first and then this one second. And you could fill out this table 3 different ways. You can fill it out in terms of a rotation or reflection. So like is this rotation here first and then this reflection? Does that give you one of these reflections, one of these rotations, right? Or the identity. Figure out which one it is and put it in the box. You can also do it by writing the cycles down and just keeping track of where the vertices go. And so you can write down the appropriate cycle here. And you can also do it where everything's written in terms of little r and m, where it's either written as 1 r, little r square, m, mr, or mr square. So see if you can fill that table out. Okay. In fact, I'm going to show you the answer here in just a minute. So why don't you pause this video and do that yourself. Come back when you're done. Well, here's the final result. Let me make this a bit smaller. So all of that will fit together on one page. There we go. And so you can see the results here. I'm not going to go over every detail here. I'll let you work on this yourselves. Hopefully you already did before you did this. But see if you can verify that this is what happens. And there's some interesting patterns in here, particularly if the table is set up right. For example, right here, this part is the cyclic subgroup. And then there's some other interesting patterns that you see. The colors actually help you see that. So see if you can get your mind around this. This actually is the smallest non-abelian group, the smallest group that has non-commutativity. Now do the same thing for the square. I think this, instead of calling this R, I've called it X for the reflection this time. Okay, and then here's the result, and then here is the result for doing the same thing with the pentagon. In the pentagon, to save space, I just only wrote the cycle notation for what's happening to the vertices in the answer here. So do these on your own. You know, really do these before, without looking at the answers, and then you can come back to these 3. In fact, I believe you can actually go to this here, and if I do there's the operation table. There's the operation table. For 3, 4, and 5. I don't go any beyond that, but there are the answers there. You can find those actually on my my site where I have this. Okay. All right. So it turns out, hopefully you notice some interesting patterns there. Each finite group of isometries, each finite group of symmetries, oh, too big. Okay. It turns out that any finite group of isometries of let me say symmetries here is either a cyclic group or a dihedral group. If the finite group of isometries contains only rotations, then it's the rotation subgroup of the symmetries of a regular polygon, and it's a cyclic group. If it contains at least one reflection and has order at least 6, then it's a dihedral group of order 2n, the group of symmetries of a regular polygon. I think I was actually correct in saying isometries here. Okay. Also notice that any reflection with the identity transformation forms a subgroup of order 2, which is also cyclic. Every dihedral group has n reflection subgroups of order 2. So this is a really good thing. Look at these dihedral groups are one of the most basic groups you look at in group theory and abstract algebra, and they're firmly planted right here in geometry and this work on transformations.